Okay, so now let's continue our discussion on maximum likelihood estimation. So I'm going to write MLE for short. And then, yeah. So last time we also talked about some properties. So let me just repeat it here. Properties of MLE. So here, this E is referring to the estimator. So maybe let me rewrite the, so this is the maximum likelihood estimation. And then that MLE is referring to the estimator, the one that you derive from data. Okay, so this is referring to a procedure, maximum likelihood estimation. This is referring to the estimator, theta hat. Okay, so last time we also talked about some of the properties, so I would like to repeat here. Let theta be a parameter of a distribution. And then theta hat be an estimator. And last time you have seen that this is a function of a data. Okay, of the parameter theta. And then we say theta hat is unbiased if the expected theta hat equal to the true parameter theta. Okay. And then our second thing regarding the estimator is that we say for this estimator is an efficient estimator. I'll just rather is efficient estimator of theta if the variance of this estimator is equal to 1 over n multiplied by I of theta, and the I of theta is called the Fisher information. I will talk more about this today. Okay, so I'll just write in short, but you have the full name from the lecture on Thursday. Okay, so there's a Fisher information. Okay, so last time we also showed Last time we also showed two results. So result 1 is that the expected, the score function, equal to 0. Okay, so that's what we showed last time. We also show another result. Can I scroll down? Okay, so another result is that the negative expected, so the Hessian is equal to the expected, the score function square. Okay, so that is what we showed. Any question regarding all the, or if you need me to scroll up a little bit? Okay, so these are all the results that you already have from last lecture. Maybe I can also add one more comment, is that the score function, or just to refresh your memory, the score function S is coming from the first order derivative of the log likelihood. Okay, so I will write log of x comma theta and then d theta. And then your Hessian is coming from the second order derivative of the log likelihood. Okay, so d theta squared, and here these log likelihood are not the joint. Okay, so not the joint version. It's referring to the single data point or single. So as long as you don't have the multiplication of n copies, that is referring to the log likelihood. So not the joint version. Okay. So if you take a look at the notes from last week, you will see that when we derive this, we do not have a multiplication of 1 to n. Okay, so I equal to 1 to n. This is the joint version. But when we're deriving the score and the Hessian, we are not deriving through the joint version. We're just deriving from the likelihood function. Okay, the log likelihood version. Okay, so that is one thing I want to point out. Any question regarding or from the material so far or from last week? Yes, I am. So yeah. Okay, so now let me talk about, I think there's one more thing I want to, so I think one thing that I mentioned in the end of the lecture is that this thing here, the negative expected Hessian that we define as the Fisher information. Okay, so here let me write it. So this is something that I mentioned in the very end of the lecture before we stop. So Fisher information, we denote it as I of theta is equal to the negative expected of the Hessian. Okay, and this is this is the definition. Okay, so the things that we derive by the end of the lecture, we end up with this result, and then I call the left hand side, this is your Fisher information. Okay, so this is the result we derive, and then this term here that shows up in our result is called Fisher information. Any question? It's just a definition thing. Okay. So today we're going to comment on our on the efficient estimated on this property here. Let me scroll up. So I'm going to comment more on this part here. Okay. So I'm going to derive some result from the efficient estimator. Okay, so one thing I want to introduce is called the Kramer-Rao lower bound. Okay, so this is the Kramer-Rao lower bound. Okay, so first of all, let's start it from an unbiased estimator. Theta hat. And then as we have pointed out, this is a function of your data. So you need data point to estimate your parameter of the distribution or your model here. Okay, so let's start it with n equal to 2 cases. And then they are independent. So x1, x2, independent. Okay, so I'm going to derive the Kramer-Rao lower bound for 2 data points first, and then we'll generalize to n data point. Okay, so first of all, let's start it with the expected estimator. So the expected of an unbiased estimator is equal to the parameter of the distribution. So we know that this equation holds by definition. Because we started with an unbiased estimator, the expected version of that should be equal to the true. And now let's write down the expected of the estimator. Okay, so here we have 2 data points, so let's start with a double integral here, and then the estimator is g1 g of x1 and x2. Okay, so here you only have 2 data points, so you're only using the 2 data points to estimate your theta hat, and theta hat is a function of the data. We only have 2, so we only have g x1 and x2. Okay, so that's your estimator, and then to calculate the expectation, you need to multiply by the density function. So you have x1, x2, semicolon the parameter, and then dx1, dx2. Here I'm just rewriting the definition of the expectation. So expectation of a function is the integral of that function multiplied by the density function. So this is the things that we introduced in week 1. when we introduce the idea of expectation. Okay, so now let's take first order. Before that, let me also point out that x1 and x2 are independent. That is just your model or the things that you assume. Like last time I mentioned that, for example, you go up to a person, you collect a data point, and then you collect another data point. So your second data point is independent of your first data point. And then the third data point is independent of your second data point and your first, okay? So that is where the independent assumption comes from, okay? Due to the independence, we can write the density function as the product of the individual data point. Okay, so I'm just rewriting the joint for x1 and x2 in terms of the product. This is due to your data is collected independently. Okay, so now let me take a derivative with respect to the expectation, okay, with respect to the true parameter theta for the left-hand side. Okay, so I'm just taking a derivative on the left-hand side here, and then for the second term, this should be equal to 1, right? I'm taking derivative of theta with respect to theta, so this is equal to 1. And then I'm going to apply the same thing for this equation here. So I'm going to write it in the following way. So gx1 and x2 is just a function of data point, all the x's. So it does not involving theta. So it will remain the same. And then we have the derivative of theta. So now we're taking derivative of a product. So here we need to use the product rule. Okay, so we take the derivative of this function first, multiply by that, and then we take the derivative of the second function, multiply by f of x, the x1. Okay, so let me write down what I was saying here. x1 and then theta. So here you can use a square bracket to wrap this up. So here's the product rule come from. Okay, and then plus the gx1, x2. So you take the derivative with respect to the second part, the x2, and then keep the first part as and then you multiply by that. This is just the product rule when you take the derivative. Where did I? Any question? I'm just applying the product rule to the product of the two functions that involving theta. Any question? And then to complete the integral dx1, dx2. Okay, so this is just coming from the, if you want, you can also wrap all the thing together. I mean, just a notational thing if you want. Yeah. Okay. And now I'm going to apply the same trick that we did last time, the log trick. Okay. So here on the left-hand side, we have this equal to 1. So the whole thing, the whole integral here equal to 1. And then now I'm going to apply the log trick that we did last time. Okay, so I think I will skip the details, but the result, we're just having the log version inside the square bracket. Okay, you have the log of the f of x1 theta. Okay, so let me wrap this one in a square bracket. So last time what we did is that we multiply and divide it by the same thing, and then we introduce the log inside the square bracket. And by doing that, you also introduce additional factor of f of x1, and here the f of x2 is coming from the original parts, okay? So by introducing the log here, you're also introducing this, okay? This is the same log trick that we applied last time. Okay, and then here I'm also going to separate the two integrals. So I'm going to stop the dx1, dx2 here, and then adding another integral here. So here you have the same thing. We apply the log trick here to the distribution for x2. And then here you have the original x1. And then this is the additional part for x2 that coming from the log trick. Okay, dx1, dx2. So the log trick is coming from the last lecture. Any question or anything, or any question regarding any of the steps here? Okay, so maybe let me pause for a few seconds for you guys to finish the notes. Okay, so essentially we are just taking a derivative of the expectation, and the expectation is just a function of g and f. And then we use the chain rule because both x1 and x2, their density function involving theta. That's why when you take derivative, you need to take the product rules. And then inside the square bracket, we apply the log trick. When we introduce a log trick, you need to introduce additional factor. So here I take the log trick for x1, so you introduce another f of x1. Here we take the log trick with respect to f of x2, so you need to introduce another factor of f of x2. Okay, so now you can see that for the n equal to 2 cases, we have arrived at the following case, to the following expression. So your estimator, g of x1 and x2. And here, for the square bracket, let me sum them together. So I'm going to write as a summation, I equal to 1 to 2, because we only have 2 data points. And then I'm going to sum the 2 terms in the square bracket in the summation here. And then I'm going to rewrite x with the index xi here. Closing the square bracket. And then you have the same x1 and x2 that is shared. dx1, dx2. Okay. What I'm doing here in the last line is that I'm just aggregating the 2 expression here by aggregating the derivative here. Because the derivative, they differ by x equal to 1 and I equal to 2. And I'm grouping them by the sum. Because the rest, they stay the same. So we have the same of all the density function. The only difference is that the things inside the square bracket. And then I'm using the summation term to square them, to add them, to combine them together. Any question regarding any of the details here? Okay, so again, we have the estimator, G, in the front. We have the density function for all of the data points. We only have 2 data points, so we have all the density function for x1 and x2. The only different thing is that you have the score function. Well, later I will talk about this is essentially the score function for each of them. Yeah. So this differ by 1 and 2, so we use a summation to group them together. Okay, so this is for the case for 2 data point. Let's general to n data point. So for general n, I'm just going to use this expression here. For the general n case, for n data point, you still have the left hand side equal to 1, except that your estimator is estimated from the data point all the way to xn. Okay, so here you only have 2 data points, x1 and x2. Now with n data point or more data point, you will have more information to estimate your to estimate the parameter. Okay, and then for the square bracket, instead of 1 to 2, you can have 1 to n. Okay, so each of the data point are contributing information for your estimation. Okay. Same thing, xi, parameter theta of that. And then for the density function, you will have all the n data point here. Multiply all the way to xn. And the multiplication here is coming from the independent. Okay, so here you should also have dx1 all the way to dxn. Okay, so this is the expression that we derive from 2 data point, the case with 2 data point. I'm just borrowing that expression to make it the n data point expression. So the difference is that your estimator is a function of n data point. Here the summation is, instead of 1 to 2, you sum up all the way from 1 to n, and then your density function, you have density for the n data point. And then the product is coming from the independent. And all of them still equal to 1. The 1 is coming from the expected, the derivative of the theta, equal to 1. Any question or comments? Okay, so now let's further analyze this expression here. So now I'm going to call the things inside the square bracket. I'm going to call this as a Q. Okay, so all the sum. So essentially this is the score function. Okay, so you sum all the score for each of the data point. I'm going to call this the Q part. And this is your estimator, so this is just the theta hat. Okay, let me write it more. So this is a Q, and this is theta hat. Okay. So now let's consider the correlation between this Q and theta hat. Okay, let's consider this quantity here. So consider the correlation between this Q and this theta hat. Okay, so now let's think about what kind of information or what kind of result that we have so far. So first of all, what we derive on the top is that the expected theta hat multiplied by Q is equal to 1. Okay, so this is what this expression is saying. So here you have all the density function. This is your estimator, this is your Q. So the expected theta hat multiplied by Q is equal to 1. Okay, so this is what this expression is saying. Okay, so this is the first piece of information that we have. The expected theta multiplied by Q equal to 1. This is coming from this expression. Okay. The second things that we know is that the correlation is ranging from -1 to +1. So the correlation of the interest here, the Q and the theta hat, ranging from -1 to +1. Okay. This also leads to another information here, or another result, is that the correlation square, the square of the correlation is less than 1. Okay. We know the correlation between -1 and +1, so the square of that is less than 1. Okay, so this is another piece of information that we know. And the third one is coming from the unbiasedness. So we know that the expected of the theta hat is equal to theta. Okay, that is by definition. We started with a unbiased estimator, so the expected of that is just equal to theta. Okay, so here are the information that we have, and now let's perform some analysis by applying this, by using these information later. Okay, any question so far? regarding the construction or the information or the things that we have here. Yes?
Could you explain the first one again?
Sorry, what?
Could you explain the first one again?
You mean to explain the first?
Yeah.
Oh, yeah. So here, okay. So if I say like expectation of the g of x is equal to the integral of the g of x multiplied by f of x dx. Do you agree with that? Okay. So now I'm going to call g of x equal to theta hat multiplied by q. Okay, so let's say g of x equal to theta hat and multiply q. And then here you can see that the theta hat multiplied by q here, I'm going to call this thing my g of x. And this part is my f of x. So the right hand side is the expectation of the theta hat multiplied by q. Do you agree with that? So theta hat multiplied by q is the function g in this case. Yeah. So the right hand side is equal to the expectation, the product, right? That's the function. And then we know that by construction we started with 1, right? So everything here equal to 1, and that is this thing here, the result 1. Yeah. Does that answer your?
Yeah.
Yeah. Good question. Thanks. Yeah. I'm just calling the theta hat and q as my function g, then just the expectation of a function, and then that is the result. And then we know that equal to 1 because of the unbiasedness. Yeah, the 1 is coming from here, from all the way to the beginning. So we know this is coming from the definition. Expected of an unbiased estimator is equal to true. When I take the derivative of this, it's equal to 1. Right. Yeah, so when I take the derivative of this, it becomes a 1. And this is the derivative of that. Yeah, so I know that. Yeah, good question. Thanks. I think maybe I will just leave this note here, although I don't like, okay. I'll just leave it for you guys, okay. Yeah. Yeah, good question. Any other question or comments? Okay, so now let's proceed to our analysis. So now, let's take a look at our correlation square. Theta hat. This thing is equal to, so now I'm going to apply the formula of the correlation. So the correlation is equal to the covariance of the q and the theta hat, okay? Divided by the variance, well, first of all is that the correlation without the square is equal to the covariance equal to the standard deviation. So now I'm taking a square, so you have the covariance square, okay? So the square is coming from this one. And then for the two denominator, you will have the variance of the q and then the variance of the theta hat, okay? And this thing we know, or by that we already know, is less than or equal to 1, right? This is coming from the square of the correlation. So what I was saying is that the correlation is equal to the covariance equal to the, okay, so covariance of x and y equal to standard deviation of x multiplied by standard deviation of y, okay? So this is the formula. When you take the square, you have the square of the covariance, and this becomes the variance of that, okay? So the standard deviation is just square root of that, okay? So this is the formula I'm using, but I'm directly applying to the square version. And we know we have an upper bound for that, less than 1. Okay, so now let's further decompose each of the terms. So the covariance square, so now we applied the covariance formula, is equal to the expected q multiplied by theta hat minus the expected of the q multiplied by the expected of the theta hat. Okay, divided by I'm going to leave the variance of the theta hat as itself, and then for the variance of the q, I'm going to write it as the expected Q squared minus the expected Q squared, okay? This is just applying the definition of the variance. The variance is equal to the second moment minus the square of the first moment, okay? I'm leaving the variance of theta hat as itself, but I'm decompose the variance of the Q in the following way. And then on the top, don't forget we have a square, okay? So this is, the thing inside the square bracket is the formula for the variance, but here we are working on variance square, so we have a variance, a covariance square. This thing less than 1. Any question? Okay, so now let's take a look at each of the terms. So I think we already know that the expected, so let's see what we already know. So we know that the first term equal to 1, that's already known. We know that this one equal to theta, that's by construction, by definition, unbiasedness. We also, I think for the rest, we don't know. Okay, so now let's further fill in the rest of the terms. Okay, so now our goal is to find what is the expected Q. Okay, and here let me introduce another bullet point here for 4. So the 1, 2, 3 is coming on the top. These information we already know. Let's fill in another information here, the 4th bullet point here. Okay, so the expected of Q is equal to the expectation from the square bracket. So what we define as Q is the thing that we construct in the square bracket. Okay, so this thing, let me copy paste to the, okay, 1 to n, and then derivative of the log likelihood, xi, and then theta. Okay, so this thing is the Q that we construct on the top. We are interested in the expectation of this Q here. Okay, and now we can see that this is the expectation of a sum, and this is essentially the score function. Okay, and then if you want, you can also add a subscript I. This is referring to the score function for the data point I. Okay, and then we are summing n copies of them. Again, expectation is a linear operation, so we can change the order of the expectation and the summation. So here we have the summation from 1 to n, and then the expectation for each of the score. So from this line here, we are just changing the order of the summation and score. And what is the expectation of score that we just mentioned on when we started the lecture and also from last week? What is the expectation of score? Okay, so let's scroll up and then let's see one of the results that we derived from last time. So you can see that expectation of the score is equal to 0. Okay, so here essentially we are summing n copies of zeros. So we know that the expected Q is equal to 0. Any question? So this is another piece of information that we know that can help in our construction of the correlation. Expected of the Q equal to 0. Any question or comments? Okay, so we also know this part, so let me check everything we know. So we know the expected of Q equal to 0. That also means the square of the first moment we also know. So we are only missing this part. So our goal here is to find a lower bound for the variance. That is actually the name come from. The Kramer-Rao lower bound. It's the lower bound for the variance of the theta hat. And then we are going to use the correlation to construct that. Okay. So right now we have most of the information. We only need the one more thing that we left is the second moment of the Q. Okay, and we can also find that. Okay, so let me write it as a as the next bullet point. So 5. Okay. So we want to calculate the expected of the Q square. This is equal to the expectation, and then sum from 1 to n, and then the individual score. F of xi, theta, and then we are interested in the second moment. So everything here taking the square inside the expectation. Okay, so for this, the square of the sum, so let's consider the scalar version for like a plus b plus c multiplied by a plus b plus c. Okay, so let's say you have a sum of 3 terms and then you want to take the square. You will end up with the following results. So a square plus b square plus c square plus any of the 2 combinations. So 2ab plus 2ac plus 2bc. Okay, so this is for the 3 terms. But right now we have n terms, and then we are just going to generalize the case for the 3 terms. Okay, so that means the okay, so I'm not going to rewrite again, just continue the equal sign here. You will have the expected. Okay, so now I'm also doing 2 things together. So first of all, I'm going to calculate the individual square, and then I'm going to decompose each of the term, because the expectation again is a linear operation. So I'm going to distribute the expectation to each of the square. Okay, so a square. Okay, so I will have the expectation of the score for my first data point, and then taking a square, and then I'm distributing the expectation plus the expectation. Okay, so maybe I can use more explicit. So this is my first data point, second data point, square, plus all the way to the n data point, and then square. And then here, any of the 2 combinations, the expected as, let's say, I'll just use I and j, multiply by the score function for j. Okay, and then so for this part is for all the I not equal to j. So this is just a cross term here for all the I not equal to j. Okay, so I'm just generalizing this expression. So when you have the sum of 3 terms here, so a plus b plus c, when you take the square, you have a square, b square, c square, and then of the cross product terms. Here, we are also taking the expectation for the n terms here. So you will have all of the, so you can consider this as a square, b square, all the way to c square. And then here, for all of the I not equal to j, so 2ab plus 2ac plus 2bc. Okay, so this one is all the cross term. Any question or comments? And then also I'm distributing the expectation to expectation of the a square, expectation of the b square, expectation of c square, expectation 2ab and 2ac. Yeah, question?
Sorry, what's like the sign have between the summation?
What is this? You mean this part here?
Yeah, what's
I not equal to j.
no, what's the thing to the right?
What is what?
That's an equal sign?
There's 2.
Oh, two.
Oh, you mean this? Oh, yeah. Yeah, here we have 2ab, 2ac, and 2bc. So you have 2 of the 2ij. So 2ab, 2ij. Yeah. That, you mean this one, right?
Yeah.
2, yeah, sorry, yeah.
Okay.
Yeah, so this is 2 copies of the cross term, 2ab, 2ac, 2bc, yeah. Okay, so now let me ask again, what is the expectation of any of the score? What is the expectation of score? 0, right? So all of the cross product term becomes 0, right? What is the expectation of score square? If you still remember. Okay, so let's scroll up again. The expectation of the score of the square is equal to the negative expectation of the Hessian. And then we also give a name to this, which is called the Fisher information. Okay, so for each of them, so the square of the score, and then after taking expectation, so all the things here equal to 0, this also equal to 0. Okay, so all the cross product term just goes away. So we only have n copies of each of the square of the score. And we mentioned that the square of the score is the Fisher information, so essentially we have n copies of Fisher information. Okay, so n of I theta. Any question or comments? Okay, so now let's go back to our inequality. Maybe let me copy paste from, okay, so this is the one that I'm referring, and now I'm just going to fill in all the terms. Okay, so for the first part, we have the expected of Q multiplied by theta. That one we already know equal to 1, right? Minus the expected theta hat, which is equal to theta, right? The other term is the expectation of the Q. And the expectation of Q from bullet point 4, we know that equal to 0. So multiply by 0. Closing the square bracket and then taking the square. Okay. Divided by, we have the variance of the theta hat. Okay, multiply by the expectation of the Q square. Okay, so here is the thing that I'm referring. So the next term here is the expectation of Q square, the second moment. And then the second moment we find out is that n copies of the Fisher information. So we have n multiplied by the Fisher information. Minus the expectation of the Q multiplied by expectation of the theta hat. Just the square of the expectation of the Q. Okay? And then again, from the bullet point 4, we have that equal to 0. So this is minus 0 squared. The whole thing less than 1. Any question? Here I'm just plugging in the terms that for the 5 bullet points that we constructed. Okay? Plug in 1 to 5. Okay, so now let's see if we are able to get a bound for the variance of theta. So we have 1 square minus over variance of the theta hat multiplied by n copies of Fisher information less than 1. Okay, so let's see what we can perform. Let me multiply variance of theta hat on both sides. We have 1, okay, so I can also remove the square from now. Oh, I think this is just the answer, okay? So this is called the Kramer-Rao lower bound. So you can see that you have a lower bound for your variance of your estimator. Okay, this is 1 over n multiplied by the Fisher information. And now let's revisit. Okay, so let me pause for a second to see if you have any question or that you finished the notes. So for the variance of the estimator, we also have a lower bound. which is 1 over n times this. Any question or comments? Okay, so now let's revisit our definition for the efficiency. So result 2, or property 2 for the estimator is saying that the theta hat is an efficient estimator if the variance of theta hat is equal to that. Okay, so now you can see that where this term is coming from. This term is actually the Kramer-Rao lower bound for the variance. So that means your estimator is called efficient if your variance of the estimator can achieve the lower bound. Okay, so your variance is always greater than this lower bound. But when the variance of your estimator is equal or achieving this lower bound, then we call this estimator is an efficient estimator. Okay, and that is how this term is coming from. So this is the lower bound. When your variance of the estimator equal to the attaining the lower bound, then we call this as an efficient estimator. Now so most of the estimator is just going to greater than the lower bound, but when it equal to that, we call it an efficient estimator. Yeah. So you are using the data point to estimate your theta hat of a distribution. And then later we'll see that when you're collecting more data point, you will getting closer and closer to the true estimator. And that is where your variance of your estimator going to 0. And then getting, so that means you are getting very, very close to the true estimator. Okay. Yeah. So here you can see that already this is a function of n. When you're collecting lots of data point, infinity data point, then this will go to 0. That means you're getting very close, or you are hitting to the true estimator, the true theta in the nature. Yeah. Any question or comments? Okay, so that is the lower bound, and then, yeah. Okay, so now let's continue. Any question or comments for this part? Okay, so that is a lower bound for your variance. And now let's continue our exercise. So I think in the previous exercise, let's see what we did. I think we developed the Poisson distribution. So this is your examples from last Thursday. IID Poisson with parameter lambda. I think we find out that the maximum likelihood estimator lambda MLE equal to the summation of xi over n. Okay, so we solve this through the maximum likelihood estimation. And we also say that this is intuitive because the expectation of data point is equal to lambda. So it's very intuitive that you have the average as your estimation or your estimator for the parameter lambda. Okay, so that is what we did in the previous lecture. So now let's examine some of the things here. Let's see if this is an unbiased estimator or not. Okay, so let's check for unbiasedness. So we need to check whether the lambda MLE here. And also one thing I want to comment is that theta here is denoting generic notation for parameter. Okay, and then depending on what distribution you're working on, replace your theta with the parameter in that distribution. So in gamma you have alpha, beta. In normal you have mu and sigma square, and then just replace the parameter, the theta, with the one that you are working on. The theta is just a generic parameter notation for any of the models. But if working on a specific model, use the corresponding parameter. Okay. So in our case, this is lambda. Okay, so maybe I'm not sure if did I develop this? Did I check that last time? Okay, so then I'll just skip some of the details. Okay, so this is also from your last lecture notes. Expected xi you have n 1 over n lambda. This is lambda, so unbiased. Okay, so this is from your lecture note from last time, where no, this is unbiased. Next, we are going to check this estimator is efficient or not. Okay, by the definition, the efficiency is saying when the variance of this estimator equal to the lower bound. So first of all, let's derive what is the lower bound here. Okay, so that means we also need to derive the Fisher information. So P of x with parameter lambda for the Poisson is, can someone just read the one that, okay, let me find it for you. So the probability mass function for a Poisson distribution is lambda raised to the power of x, e raised to the power of negative lambda, and then x factorial. Okay, so this is the probability mass function. Okay, to get the Fisher information, we need to start with the log likelihood. So log of the P of x is equal to x multiplied by log of lambda minus a lambda minus the log of x factorial. Any question regarding this part? Okay, so I'm just taking the log of the bunch of product terms, and then you will get the summation here. So x multiplied by log of lambda multiplied by a plus a log of the exponential of that, so that's why they cancel out. We have negative lambda. This one in the denominator, so we have a minus log of x factorial. Okay, that is the log likelihood. To get the Fisher information, we need to take the first order derivative of the log likelihood. So the first order derivative, you will have x over lambda minus a 1 minus a 0. Okay, so that is your first order derivative with respect to lambda. Let's take another derivative. So another derivative or a second order derivative for the log likelihood. So if you want, this is also lambda negative 1 multiplied by x minus 1. So for the second order derivative or another derivative of this term is that negative 1 multiplied by lambda negative 2 multiplied by x. Okay, any question or comments regarding some of the derivative or the log transformation here? Let me pause for a second and then to see if you have any question for the log transformation and the derivatives. It usually takes 7 seconds for people to come up with a question. So let's pause for 7 seconds. Yeah. All good? Okay. So now we are ready to to calculate the Fisher information. So the Fisher information, again, by definition, so here I'm going to put I lambda as the parameter, I theta, is equal to the negative expectation of the Hessian. The Hessian is referring to the second order. Okay, so I'm going to plug in the second order derivative here. So this is just the definition part. Okay, so the minus sign cancel out. You have 1 over lambda square from this constant here multiplied by the expectation of the x. And what is the expectation of x for the Poisson random variable? It's lambda, so you multiply 1 copy of that. Your Fisher information is 1 over lambda. Any question or comments? Okay, so that's your Fisher information. And now let's calculate the Cramer-Rao lower bound. So Cramer-Rao lower bound for a Poisson random variable is 1 over n times the Fisher information. So this is 1 over n multiplied by 1 over lambda. Okay, so that means the Fisher information for a Poisson distribution is lambda over n. Okay, so now you have the Cramer-Rao lower bound. What do we need to do next to check efficiency?
The variance.
The variance of the parameter of the estimator, right? Yeah. Okay, so now I have the Cramer-Rao lower bound. We also need to calculate the variance of the estimator. So variance of the MLE here, and then if the variance equal to that, that means our estimator, our MLE estimator, is an efficient estimator. Okay, so variance of summation from 1 to n divided by n. Okay, so I think by now you should be already very familiar with how to work on these things. So when you pull out a constant, you have 1 over n squared. They are independent, so you have the summation outside, and then you have the variance of I. So here everything is coming from the IID assumption, okay? So 1 over n squared. They are identically distributed, so the sum of them, so you have sum of n terms, so that is another n coming from. And each of them are identically distributed, so you have the same variance of xi. What is the variance for Poisson random variable?
What is it n square?
Sorry?
What is that n square?
So when you plug in a constant outside the variance, you need to take the products. You need to take the square. If you want to show the proof, you can get this from the moment generating function. Yeah. So this is kind of like when you put a constant 1 over n outside. So for expectation, when you put 1 over n outside, it's just 1 over n. For variance, 1 over n, when you put it outside, it's 1 over n squared. Yeah. What is the variance for the, also lambda, right? Okay. So the variance of xi is lambda. You have n copies of them because they are identically distributed. You have n copies of that. This is equal to lambda over n. So here it attains the Cramer-Rao lower bound. Okay. So we can draw the conclusion. This unbiased estimator. So first of all, this you need to. Okay, so let me finish this. Okay, so this is an efficient estimator. Okay, so the concept or the idea of the efficient come after the unbiasedness. Okay, so an estimator need to be first unbiased before you discuss whether it's efficient or not. So here we first check that it's unbiased, so we are able to discuss efficient. If it is not unbiased, then there's no need to discuss whether it's efficient or not. Okay. So it attains the Cramer-Rao lower bound. We know that this unbiased estimator is also an efficient estimator. Okay, so there's another thing I want. Okay, so let me pause here to see if there are any questions or comments. Yes.
Would there be, so if this is an efficient estimator for a sum of Poisson distributions, are there other efficient estimators?
Then you need to check for everyone everything you derive. If we have time, then maybe we can work on that distribution later. Yeah. So for every distribution, you need to check whether it satisfies the properties that we just specified, that we define here, and then you can claim. So here we check that it equal to the lower bound, so it attained the lower bound is an efficient estimator. Yeah. So for every estimator, you need to define. Yeah. Yes.
In section, we learned that efficiency means that the distribution is gathered around the true data. So then, why is it that when the variance is the Cramer lower bound, that means it's clustered around? theta.
I don't quite get what you. Can you repeat your question? So here, I think we are. Yeah, go ahead.
So, in the more like conceptual sense, we learned that the efficiency means that the distribution is clustered around the true theta. So then, my question is, how is the Kramer lower bound a marker of that concentration? Like, how does it mathematically correlate?
I still feel like that's two different questions. So, here you're saying, okay, so I'm not going to say what distribution is for now, but let's consider this is the, let's say this is the true, okay? So I would say, the Kramer lower bound, I would say with more data point that you collected, then you are more centered around your true parameters. I think so. When you have more data point, you have smaller variance, and then it will get closer to that. And then your question, I still don't get it. What did your? So, for example, this one, when you have wider variance, this is coming from, let's say, n equal to 1,000, and let's say this is n. This when you have 10,000 data point, you will get a very closer to your unbiased, to the true parameter.
Oh, okay, so we're just reducing variance. Yeah.
I'm not. I still don't quite get what's your question. Can you say that again?
No, I was wondering, like why the Kramer lower bound means that it is clustered near the theta, but we're just trying to minimize the variance, so naturally the spread is narrower, so then obviously it's closer to the true theta.
I don't think the variance means that it's closer to the true variance.
But it like tightens around it as the n becomes larger.
So, if I understand correctly, so first of all, the variance of your estimator is greater than that. So it doesn't mean that. So I mean, when clustering around the true parameter, it means that it's unbiased, right? Your expected value of your theta hat is getting close to that. So getting close is.
That was the definition that was used.
Then, I mean, whether it concentrates. So let's assume for now that your estimates are already unbiasedness, right? So it's centered around the true value. Whether like if the center mass is clustering in the true parameter, that would depending on the variance of the theta hat. I think the Kramer lower bound has something to say with this one. This is just a lower bound for that. But whether it's clustering, like getting closer to that true value, that would depend whether how large or how small your variance of the theta hat is. It's just that this thing has a lower bound is equal to that. Yeah, then it becomes wider. And then if this goes down, then it will become narrower. Yeah, but it just there's a lower bound for this terms here. This is also a random variable actually. Yeah, this is a function of x, and then x are random variable. You are calculating the variance of that. Yeah, so whether it cluster in that, and let's say unbiased, whether it cluster to the true, it depends on how large the variance is. Yeah, but it's just that there's a lower bound for that. You will never go lower than that. Yeah, but when n, let's say, go to infinity, then you will see that the lower bound will go to 0. But that is referring to the lower bound. That is not referring to the actual how the variance center, like whether it's wider or narrower. I'm not sure if I understand your question correctly. I might have misunderstood your question as well.
No, I don't think I was properly understanding the lower bound, but that explains.
Yeah, the lower bound is just a thing, like a lower bound, that this thing will never be lower than that. Yeah. But whether it will get narrower or wider, it's just depending on this quantity here. Yeah. Yeah. I might have misunderstood your question, or maybe I'm not able to answer at this moment. Yeah. Any other question or comments? Oh, yes, go ahead. Sorry. You can yell at me. Yeah.
I was wondering how we determined that the expectation was unbiased, or if we did do that. If we didn't.
Which part? What do you mean?
For the example you just did.
Oh, yeah. So if you want to check the unbiasedness, you just take the expectation for the parameter of your estimation, of your estimator. So this one, so expectation of theta hat equal to theta, then this is unbiased. This is what we did to check the unbiasedness. So the definition of unbiasedness is expectation of theta hat equal to theta. Okay? So here we check expectation of that after manipulation we get that equal to theta. So this is unbiased. So check. Yeah. Yeah. Yes.
You probably might have went over this, but could you define again what a lower bound is?
Oh, okay. The lower bound is just saying, one way to think about this is that let's put a here. It's just saying all of your, so this thing here will never be lower than that, but it can take any values from A. So that is the, so let's say X is in let me put, so if you think about the support for Poisson distribution, then the lowest value that you can get is 0. Then that 0 is the lower bound for the support for that X. It's just that something like you can get anything in above that lower bound, but just not lower than that. So that is kind of like the idea for lower bound. I'm not sure if that answers your question. It's just the smallest value that this thing can get to.
Right.
Yeah.
I get it now.
Yeah. So for example, the support for Poisson is all the zeros, 1, 2, all the way to infinity, but the 0 is considered as the lower bound for the values that you can get. Yeah. So that would also be a lower bound. Okay, so one more thing I want to mention is that the theta MLE here follow a normal or approximately follow a normal distribution centered around the true value and then 1 over n times the Fisher information. Okay, so there's a proof for this when n is very large, but so in practice you can just use this normality to get you can just apply this normality. And the usage of this normality is that you can construct a confidence interval of your parameter theta. And this is what you can do in practice is just plug in the theta MLE plus and minus the quantile. So here I'm just referring the 95% on both sides, so 0.025 and 0.975, depending on your alpha, or 1 minus alpha over 2. Or maybe let me just put more precisely, 0.975 plus and minus, okay? So I'm taking the right-hand side, and then you can do plus and minus, and then 1 over n times the Fisher information, but here plug in the estimator that you construct, okay? Square root for standard deviation. Okay, so this is what you can do in practice. And this is when n is large enough, you can prove that this is going to normality. And then in practice, you can just plug in this one. And then, so here, this is the thing that you plug in, that you have an expression and then use data to plug in. And then for that, you can also plug in the Fisher information. Yeah. And then using the quantile, you'll get the confidence interval. And this is the usage for this normality here. You can get an estimate, or you can get a confidence interval for your true parameter. Okay. It's just a usage of that. Any question or comments? If not, then maybe let's do one more examples.
What did you write below the C?
Sorry, what?
What did you write next to the C?
0.975, the quantile for a standard normal. So the quantile of standard normal. So the 97.5 quantile of standard normal. Okay. Okay, so let me also add in one more. Okay, so let me also add in one more properties for the estimator. Okay. So we call theta hat is consistent. So the first one is referring to unbiasedness, the second one is for efficiency, the third one is called consistent if the variance of your theta hat, your estimator, goes to 0 as n go to infinity. Okay, so this is another properties that we, or another, you can always consider this are just some adjective that you use to describe your estimator. You can describe it as unbiased, you can describe it as efficient, you can also describe it as consistent. Okay, for different adjective that you use, just as long as they follow, they satisfy these conditions, then you can use the words to describe it. Yeah. So unbiasedness, efficient, consistent. Yeah. So for example, a quick thing we can check. So this is the variance of the lambda. So lambda over n. So when n go to infinity, then this will go to 0. So the variance of your estimator will go to 0. Then you can say that this estimator is a consistent estimator. It's consistent. It goes to 0 when n go to infinity. Okay. Any question, comments? Yes.
Isn't the efficient estimator unique for each distribution?
What do you mean by unique? Or what do you mean by, yeah?
If you could construct an efficient estimator, then when you take the expectation of that estimator compared to another estimator for the same distribution, you could show that the two functions have to be the same. Is it possible there's another efficient estimator for the Poisson distribution? It's different from.
You're just saying the efficient part, right?
Yeah.
Okay, so let's say there are two unbiased estimator, and then actually I'm not sure. So what you were saying is that you want to verify the uniqueness of two efficient estimators. I'm not sure. Yeah, but one thing I know that is that you can have different unbiased estimator. Yeah, but for efficient, then I'm not sure. Yeah. Yeah. That's a good thing to think about it, but I don't have an answer for that. Yeah. Yeah, but if you have multiple, then you can all use this to verify whether it's efficient or not, and then that will give you. So if you can find two that all attain the lower bound, then you have your proof for they are not unique, right? You can just use this to check. Yeah. Okay, so the course ends at 55, right? 15 minutes, right? Okay, so maybe do you guys want a break, or I'll go for another examples? It's just 15 minutes. Is that okay for everyone? Okay, so I'll go for another example because it's just a first part of one examples. Okay. So this one we are going to work on continuous distribution, IID, with normal, mu and sigma squared. Okay, so what we did previously for the Poisson is discrete random variables, and now we are working on the continuous case. So the question for this examples is that find the MLE first of mu and the sigma square. Okay, so that's the first step. Also, check the MLE whether they are unbiased okay, and also check whether they are unbiased and then if they are unbiased, you can check whether they are efficient, and then if they are consistent. Okay, so that is the things we want to work on this exercise. Okay, so now let's find the MLE for theta, for mu here. F of x with parameter mu and the sigma square equal to 1 over square root of 2 pi exponential negative 1/2 x minus a mu. You can write different way for your notation, but this is the one I'm going to use for now. So I'm going to put the sigma square here and then put the x minus mu square here. Okay. You can also bring the sigma square inside this one if you want, but this is the one I'm going to use. Okay, so let's find the MLE for mu hat. To do that, let's construct the likelihood. So here I'm going to use the capital L for the joint likelihood. And here, although there are two parameters, I'm just going to focus on one for the mu for now. Okay? Based on independent, this is the product from 1 to n, and then f of xi with the mu and the sigma square. Okay, so the joint likelihood is equal to, so here I'm going to write, oh, am I missing? Yes, okay, I did miss something, there's a typo. This is not the standard normal case, so you have the 2 pi sigma square under the square root, okay? When it's the standard normal, the sigma becomes a 1, so that's why it disappears. But this is not a standard normal, okay? So there's a mu and sigma square. I mean, when sigma square equal to 1, when it's standard normal, this disappear. But don't forget there's a sigma square, okay? So you have 2 pi sigma square raised to the power of negative n over 2, okay? So the n is coming from the product, okay? Exponential negative 2 times 1 over 2 sigma square, and then here is also the summation from 1 to n xi minus a mu. xi minus mu, and then square. Okay, so I'm just multiplying n copies of that. Okay, so the power of this part, the n, is coming from n copies of the products of these things. And then product of the exponential is the exponential of sum. So here you have the sum of them. Now let's take the log version for the log likelihood. We are going to solve this problem in the log version. So use a lowercase l of, so this is a function of a parameter, so a function of mu. Okay, taking the log, you have the factor or the power in the front, and then log of 2 pi sigma square minus 1 over 2 sigma square summation Okay, any question regarding any of the concepts, the capital L, the lowercase l, and also some of the transformation here?
The lowercase l again, could you just explain that a little bit?
Yes. So, okay, I can also add one more step. I mean, then probably it will make sense. So the lowercase l is equal to the log of the uppercase L. Okay. So essentially we're just taking the log transformation of this line to obtain this line here. When you take the log, the power will go in the front. So you have the negative n over 2 and then log of the things inside the parenthesis. And then the log of this one will just cancel out with this exponential. So whatever remaining in the parenthesis will be carried on here. Any question or comments? Yes?
Does unbiased, efficient, and consistent all mean the same idea, or are they all distinctly different?
They are different. So for the unbiasedness is that the expectation of that parameter, of the estimator, equal to this one here. But then it does not tell you whether the variance of that equal to that. So they are different. So if you want to check for efficient, then you need to check their variance. So here we are only checking the expectation. And then for the second property, you need to check for the variance. Yeah. So then they are not saying the same thing. You need to check them individually. You need to check first unbiased, and then you can talk about whether it's efficient or not. And then you can talk about consistent or not. So that's three different things. You need to check step by step. Yeah. For the first step, you check the expectation. For the second step, you need to check for the efficient, you need to check the variance. For the consistent, you need to check whether the n is showing up in the denominator or not. Yeah. Then when you go to infinity, it becomes 0. So there are three different things you need to check step by step. Yeah.
They all have to be checked in like a certain order, or can they all be?
I would say you need to check in the certain order. So for example, you can only check whether it's efficient or not for an unbiased estimator. If the estimator is not unbiased at all, then there's no need, there's no efficient to talk about it. Yeah. Efficient is only talk about unbiased estimator. Yeah. You have other estimators that are not unbiased. Yeah. Does that
The
end?
same goes with consistency too. It's like if it's not efficient, then you can't say it's consistent.
That's a good question. Let me think about it. I don't think, to me, as long as the n is showing up in the variance term, then you can say that's consistent. But that might not be an unbiased estimator. So it could also happen, I would say. So the variance of an estimator will have a denominator n, but that might not be an unbiased estimator at the beginning. Yeah. Yeah.
Thank you.
That's a good question. I will need to think about it. I'm not sure, but to me, the consistent part, I mean, yeah. You can also have like some other not unbiased estimator, but maybe it's consistent, yeah, when n is showing up in the denominator. Yeah. Okay, so maybe I'll just finish these examples for the mu. Okay, so to calculate the MLE, you take the derivative of the lowercase l, the log of the joint likelihood with respect to the parameter of interest. Okay, so now taking the derivative with respect to mu, the first thing is 0 because the first thing does not involving mu at all. Okay, minus 1 over 2 sigma squared, that's a constant. Okay, and then summation from 1 to n. And here we started to encounter things that involving mu, so we can take the chain rule for the derivative. So derivative of that, you have the 2 multiplied by xi minus a mu. Okay, and then for the mu, you have a negative sign, so this will be a plus. Okay, so I'm changing this minus sign to a plus. Okay, let's further simplify this thing. You will have 1 over sigma squared, so the 2 cancel out. Summation from 1 to n, and then this is xi. Okay, so I'm also going to break the parenthesis here. So the summation of xi minus the n multiplied by mu. Do you agree with that? I'm just break the parenthesis there. Okay, so sum of xi is one term, and then sum of mu's is also one term. And then because the mu is just a constant, you have n copies of them, so you have n multiplied by mu. Okay? To find the maximizer, set the gradient equal to 0. That's how you solve for maximizer. Okay? Now, you can simplify this by multiplying sigma squared on both sides. You will have sum from 1 to n xi equal to n multiplied by mu. Okay, and then the maximum likelihood estimator for the normal distribution of mu equal to summation of xi over n. Okay, this is also an intuitive result. You want to find the mean or the expectation for the normal random variables. You just take the sum divided by n. Okay, so I'll pause here and let me know if you have any question. Okay, so let me pause the video.